Hi guys, our project is on the air gap technique and its uses when a gridded technique is not possible. We will be making reference to an article by C. Shan titled Dose Optimization in Pelvic Radiography by Air Gap Method on CR and DR Systems, a phantom study. We're going to talk about the physics behind this method. We'll be going through the differences between Compton scatter and photoelectric effect, image contrast, the air gap technique, and how it is different from film and digital imaging, magnification and how to fix it, and different technical factors that can be used. As it was mentioned before, we are reviewing the article Dose Optimization in Pelvic Radiography by Air Gap Method on Computer Radiography CR and Direct Radiography DR from Elsevier. This study looks at how feasible it is to replace the anti-scatter grid with the air gap technique for pelvic examinations with the purpose of reducing patient dose while keeping image quality. The highlights of this article were that 10 centimeters air gap was found to be substitute to replace grid in pelvic rando and CR and DR. Rando is the type of phantom they use in the study. Also, that over 68.6% of those reduction effects were achieved at the ovary and testis region, and also over 76.4% of reduction in effective dose were achieved by both the tested regions. The dose reduction by air gap technique method was found to be more pronounced in the CR than in the DR.
In our module, it states that at high beam energies, more scatter is directed in the forward direction, and hence you get more scattered photons incident on the detector. Since the X-rays we use are polyenergetic, there is always a chance of Compton scatter and photoelectric effect to occur. Photoelectric effect is when a photon uses all of its energy to collide with an inner shell electron, and the electron is ejected. Photoelectric effect happens at low range kVp. X-rays that undergo the photoelectric effect add diagnostic information to the image because they are generally absorbed by materials with a high atomic number, such as bone. This causes lighter areas on the image. Compton scatter is when a photon collides with an outer shell electron of an atom. By hitting the electron, the energy of the photon is redirected. Scattered X-rays retain 65% of their initial energy, so they still have a fairly large penetrating power. This allows them to be able to strike the image receptor, which will degrade the image. Compton scattered X-rays contribute no useful information to the image. It can pass through the patient and contribute to staff dose, or it can undergo one of the 4 attenuation processes to contribute to patient dose. The image receptor is unable to decipher the difference between scatter and an X-ray that came straight from the tube. Compton scatter is the predominant scatter in diagnostic X-rays. Contrast is the degree of difference between the light and dark areas on a radiograph. This contrast allows us to be able to see the difference between anatomical structures. When there is too much scatter hitting the image receptor, the contrast decreases, When this happens, it degrades the image. A technique used to avoid too much scatter is to use a fixed KVP and a variable MAS.
The air gap technique is most often used with large anatomical areas, as these tend to produce the most scatter. Getting rid of the scatter improves our contrast. However, this may only be noticeable on film screen image receptors when compared with digital image receptors. This is because a digital imaging system have computer processing that function to produce an image with appropriate brightness via a histogram. As a result, selecting a correct technique when using an air gap method is more important when using a CR system than a DR system.
The air gap technique and scatter control. The air gap technique is based on the simple concept that much of the scatter will miss the image receptor if there is increased distance between the patient and the image receptor. The greater the gap, the greater the reduction in scatter reaching the image receptor. Similar to grid, contrast is increased, the number of photons reaching the IR is reduced because less scatter reaches the image receptor. And to overcome the increase in unsharpness, an increase in SID is required.
Magnification depends on three factors: the source to image detector, abbreviated as SID, the source to object distance, abbreviated as SOD, and the object to image receptor distance, abbreviated as OID. The air gap method uses an OID of 10 centimeters to 15 centimeters. This distance causes magnification of the body part that is being imaged. To avoid this magnification, the SID needs to be adjusted so that it is further away. By doing so, the magnification is decreased and the body part is closer to the original size. There is two different calculations that can assist when trying to fix the magnification caused by the air gap method. The first one is SID equals SOD plus OID. By adding the SOD to the OID, you will get an SID that will adjust for magnification. The second calculation is used to calculate a new MAS to maintain the same penetrating power at a different SID.
When using the air gap technique, we move the image receptor roughly 10 to 15 centimeters from the patient. To accommodate for this increase in OID, we need to increase our MAS as SID will be also increasing to accommodate for the magnification we created. We usually need to increase the MAS by approximately 10% for every centimeter of the air gap. The change in technique factors are similar to those used for an 8:1 grid, however this method can be applied to replace higher grid ratio images. Despite an increase in MAS due to the increase in SID, the dose to the patient is still relatively the same when trying to maintain a uniform density. Therefore, increasing the source to image receptor distance to 300 centimeters from 180 centimeters improves spatial resolution with no increase in patient dose. When using an air gap method, we need to ensure we are choosing the correct KVP. As we increase KVP, the number of photoelectric interactions decrease while the number of Compton interactions increase. The air gap technique is not as effective in high kVp settings because the scattered X-rays are aimed in a more forward direction. In projections where the kVp selected is below 90, the scattered X-rays are generally directed more to the side, and therefore the air gap technique is more effective in removing them. This is another reason as to why we need to increase our MAS when using this method.
Alright, welcome back, class. They are setting up for the air gap method. So we have a 10 centimeter sponge here, which is elevating the pelvis 10 centimeters from the detector, creating our air gap so that the scatter is going to come out away. And then we need to increase our SID so that we don't get magnification. Alright, so this is our original setup with the SID at 100. You can see here that the pelvis is magnified. And then we adjusted the SID and it demagnified our air gap method. Yeah. These are our references. We hope you enjoyed our presentation.